The topic of this lecture is the uh, use of what is called state space representation to capture the dynamic of a system. State space representations are there to help you with not only looking at input to output properties of a system, but also look at what happens to the state of the system. In essence, state space representations are fundamentally not very different from differential equation representations. And in many cases, they are almost the same. State space representations are there to help you find, as I said, certain characteristics of the system, in particular modes in flexible systems. There are other applications as well, and that includes the numerical integration of differential equations. There are several interesting properties of state space representation. In fact, many more than can be handled within the scope of your course. The purpose of this first lecture is to familiarize you by going through examples after I have described to you the fundamentals of what a state space representation looks like. So when we talk about state space systems, we have immediately the notion of state that appears. As we will see later, the notion of state is fundamental in the study of general dynamical systems. However, for today's purposes, let us simply jump into the definition of a state space system. So a dynamical system in state space looks like this. It looks like a differential, it has a variable x, which is a vector. It has an input u, which is usually a number, sometimes a vector, but rarely for what we're going to talk about. And we have an output y. And again, usually a number, sometimes a vector. And of course, u here is the input. And the whole thing is driven by the following differential equation, d dt of x is equal to a times x plus b times u. Now, and y, by the way, is equal to c times x, possibly plus d times u, but it will not be always the case. Now, in this case, since X is a vector, A is a square matrix. And B is usually a column vector. It has as many entries as the size of X. So if X is real in this with n entries, then B will usually be real with n entries if U is a number. And likewise, if Y is a number, then C is a row vector of dimension n. So this may look like a specialized formulation of a dynamical system, but in fact it is very general, and any linear differential equation can be written like that. Okay, so let's go through some examples, and then we'll go through some interesting properties. So suppose that you consider the differential equation x dot equals u, which is really the simplest one we can think of, and one we have encountered before. Then we simply can write that x dot equals ax plus bu with a is equal to 0, okay, so it's a number, it's 0, and b is equal to 1, okay. I forgot to say the output, okay. We could simply say y is equal to x, or in other terms, c is also equal to 1. Let's now look at more complex equations. One of them could be x double dot plus kx plus bcx dot is equal to u. Okay, we have seen that this is a mass spring dashpot or dashpot system. Okay, now this system cannot be written as immediately in state space form unless you define that your vector x is going to be x dot, and then you're going to have that d dt of x will be equal to x dot and x double dot, but x double dot is equal to minus kx minus cx dot plus u. Okay, so I can rewrite this as d dt of x is equal to 0, 1 minus k minus c times x plus 0, 1 times u. The only particular effort that we had to make was to decide that our state would be made of both x and x dot. It is a rule that when you see many different derivatives of the same quantity here in a differential equation, then it is important to account for and to add more than just the variable of interest in order to transform this second order differential equation into that first order differential equation. Now, why do you call this one second order? Because we see second derivatives of the variable involved appear. Here, we see only first derivatives of the variable involved appear, but of course the variable contains both an x and x dot. Okay, so that is the state of the system. X is the state of the system, and the resulting differential equation is first order. Let's look at other examples. So one possibility would be what happens if you have coupling between two different variables. So you could imagine two masses, okay, connected by a spring like we've seen before. Okay, this one's position x1, that one has position x2. We can write that x1, I would assume that the masses are 1, okay, and the stiffness k is 1 as well. Then we have x1 dot is equal to minus x1 plus x2. Okay, oh, and of course I forgot an input u here, a force. Okay, so plus u. Okay, that's x1 double dot. x2 double dot will be equal to minus x2 plus x1, and that's it. Okay, so how do you write that in state space form? Well, you introduce the vector x made of x1 dot, x2 dot. Why? Because you see first and second derivatives of x1 and x2 appear, or to be more precise, we see up to second derivative of x1 and x2 appear. By doing so, we can write that d dt of x will be simply equal to x1 dot and then x1 double dot, which is minus x1 plus x2 plus u. Okay, d dt of x2 is equal to x2 dot, and d dt of x2 dot is equal to minus x2 plus x1. And if we want to write this in matrix form, we just construct the matrix A so that these expressions are A times x, which is x1, x1 dot, x2, x2 dot. So I'm going to just summarize it at x. And what I get is that it will be 0, 1, 0, 0. dt of x1 dot will be minus x1 plus 0 times x1 dot plus x2, okay, plus u. We will take care of it later. And then the last one will be 0, 0, my mistake. 0, 1, and the last one will be 0, my mistake again, 1, 0, minus 1, 0, okay, plus b times, so this is A, and plus b times u, my b becomes 0, 1, 0, 0 times u. Okay, so that's my b. Okay, now depending on where I read my position, say I read my position here, y is equal to x2, then I can write that y is equal to cx plus du, where c is 0, hold on a second, 0, 1, 0 times x. Okay, and so by doing so, we see that we can write this system of two differential equations into a set of a single differential equation. And by the way, these were second order differential equations. And here we have again a first order differential equation, since we see only one derivative up here. Alright, so let's go through yet another example. So one of the possibilities is to use a pure mathematical expression like x triple dot plus 2x double dot minus x dot plus u equals x. Okay. Not surprisingly, we define our state vector x to be x dot x double dot, and we get that d dt of x will be equal to 0, 1, 0, 0, 0, 0, 1, 0, and then, my mistake, there are too many zeros here. So let me erase that. I think that we have too many zeros here. Okay. If we go back here, the final element will be x triple dot. The dt of x double dot is x triple dot, which is going to be x plus x dot minus 2x double dot. Okay, so this is a 1. And this is going to be times x. And of course, we need to add the input u, which will be 0, 0, minus 1 times u. Okay. If you write y is equal to x dot, okay, then y is equal to, for change, 0, 1, 0 times u. Okay. And here is your state space representation for this third order differential equation. Notice one thing, which is the order in which you count these x dot, x double dot doesn't matter. You could define x prime, another state variable, to be equal to x dot x double dot instead. And still define your differential equation, d dt of x prime. It gets a little bit more complicated, but it is a matrix times x prime plus another matrix times u. Now let's populate this matrix. d dt of x double dot, that hasn't changed, so this is the thing here. However, d dt of x dot, that's x double dot. Okay, so d dt of x dot will be 0, 0, 1, which pulls out properly x double dot, but d dt of x will be x dot, so d dt of x will be x dot, and this will be a 1, 0, 0, and d dt of x double dot will be, in this case, x triple dot, which is, on the one hand, plus x dot, on the other hand, hold on a second here, plus x, okay, and minus 2x dot. Okay, so now when you compare this a prime with that a, okay, you see they are different. However, of course, they talk to each other by means of a permutation of rows and columns, and it is equally well understood that you can use this order or that order of the so-called states and we'll see later that we can in fact simplify and use like specific orders of states. In fact, linear representations of states that you're going to be using very, very often. Okay, we're gonna sort of do change of basis. The purpose being for you to get an analytical expression for the solution to this state space representation of dynamical systems. All right. Now, a few words about why we call that state space. Okay. The state is this very notion that it sort of summarizes the where the system is. Okay, when I say what is your state, I'm asking what state are you in? Of course, you could answer I'm in Georgia or I'm in Massachusetts, but if I were wondering about the state of your health, you could give me a report saying that my health is pretty good. I've got a spot here and maybe an aching tooth there. And basically, it would be sort of a report on the condition. Okay. That applies also to the state of a car or the state of the union. The state of the union is somehow a report to Congress of the general condition of the republic as perceived by the president. Now, so intuitively, the state is a report or a summary of where the system is. Okay. It may, by the way, be also your patient folder at your doctor's place. Okay. Or at not only your doctor, but also your lawyer. Okay. So what is the equivalent to that for dynamical system? Well, the state is defined as all the needed information to get the system going from there. So let's see what that means. You take your system and you say my system is x dot equals ax plus bu. And I'm saying, okay, let me say x of t I know at some time t0. Can I forward time in such a way that I can predict x at any time in the future? Well, of course, you need to know u for t greater than or equal to t0. But except for that, do you need any more information than x at time t0 and u at time greater than t0? And the answer is no. Why? Intuitively, to solve the DCQ, you can write that if x dot equals ax plus bu, another way of writing it is that x of t0 plus dt minus x of t0 divided by dt is equal to a x of t0 plus bu of t0. Okay, that's sort of an approximate expression for x. And what you get is that x of t0 plus dt is therefore equal to x of t0 plus dt times ax of t0 plus bu of t0. Okay. In other terms, x of t0 plus dt is entirely defined by knowing x at time t0 and u at time t0. And then, of course, once you know x at time t0 plus dt, you can compute x at time t0 plus 2 times dt. And it will be a function of x of 0, x of t0 plus dt, and then other things like that. But my point is that x of t0 and then u one time is equal to greater than t0, okay, is all you need to know in order to predict what the next condition of the system is going to be. Okay, so x is the state because it precisely summarizes the condition of the dynamical system at any time, and therefore allows you, for example, to restart your system from that condition. So let me give you an analog to that. Okay. So when you put your computer to sleep, so the RAM is erased. Okay. And if you remember, for example, on a Windows computer, what you're going to see is, for example, like little bars going before the computer actually goes to completely to sleep. And what does happen? Okay, well, what happens is that while these bars are being drawn, okay, all the relevant information about your current open applications, document, URLs, window positions, etc., are stored on the disk. Okay, and what they represent is all the information needed to restart computer where it was left. And so it is literally the state of the computer. Okay? So, because of that, I mean to say that the state of a system is not only something that you will encounter while studying linear dynamical systems, but you will see this very general notion in just about any system for which time counts. For those of you who keep going in the direction of dynamical systems, this will be sort of a way of life at some point. For those of you who are interested, say, in fluid dynamics, it will also be a way of life. What you want as the state is the pressure distribution, the temperature distribution, the velocity distribution. For example, to define a state, there can be not enough information. Not enough information exists. Okay? In the differential equation, x double dot plus 2x dot plus 3x is equal to u, okay? X dot is not enough information to define a state. However, there is never too much info. Okay? So for example, you could define your state to be x, x dot, x double dot, and u. Okay? It is okay as state. It just happens to be redundant. Meaning there are things that you don't need to remember in here. To be more precise, you can, for example, cross out x double dot and u. Okay? But if you keep them, you're fine. So, I mean, this is a very important concept that states are never too much. And if you are hesitant about your state, better have too much than not enough. Okay? So, there are a few important notions that come with the notion of state space representation. One of them is so the relationship of state space representation and how they can be used in integrating numerically differential equations. So suppose you've been able to write your system in differential, in state space form. That you have a system which is written as d dt of x is equal to ax plus bu. Okay, I mean it could be in lowercase, just to point out that u is, for that purpose, a number, okay, a scalar. Okay, then I can use that to actually numerically integrate the corresponding dpq. How does it work? Well, so I did it already. If I know x of 0, okay, I can approximate d dt of x to be x of t plus dt minus x of t divided by dt. And I'll say that this is equal to a times x of t plus b times u of t. And I get that x of t plus dt minus x of t is equal to, sorry, I just going to put the x of t on the other side. It will be equal to a times dt plus identity times x of t. Okay, identity times x is just x, plus b dt times u of t. Okay, so since this is true at any time dt, okay, I can write, for example, the recursion that x of k times dt is equal to I'm going to a times dt plus I x of k minus 1 dt plus b times dt u of k minus 1 dt. Okay? Given that I have x of 0 and I have the corresponding u of 0, okay, this is a recursion which allows me to get x of k times dt for any k given the previous values that I have computed for x and the values of u. So this is a way to numerically integrate the differential equation. Now in this case it's named forward Euler, and it is not the most accurate integration method. For one thing, it's because this approximation of the derivative is kind of rough. You want to work with better approximations of the derivative in order to obtain things that are better than forward Euler. But for practical purposes, each time you want to use and integrate a differential equation, and you do it as opposed to you call a routine from MATLAB to do it, you can use forward Euler, just pick dt very small. Okay? It's like the integration step. Okay? Right. So, that said, let's talk about more interesting things. One of them is the relationship that exists between state space and transfer function. So, the state space representation, for example, for the system x double dot plus x dot minus x equals u, okay, we read as d dt of x. Now I have defined x to be, let's change things a little bit, x dot and x. So I invert the role of x and x dot. So in which case d dt of x will be equal to, well, we start with the bottom vector, it will be x. So it will be d dt of x will be x dot, so it will be 1, 0, and d dt of x dot will be x double dot, which is minus x, so sorry, plus x. Okay, so plus x minus x dot. Okay, so that's A, the A matrix, and then plus B times U. Okay, and it will be 1, 0 times U. Okay, now if you went through the Laplace transform here, what would you get? You would get something along the lines of, I assume all initial conditions are 0, and I obtain s squared plus S minus 1 times X equals U, or in other terms, X over U is equal to 1 over S squared plus S minus 1. Okay? Now what if I go through this instead? Well, so this is a general expression for d dt of x, or a specific example of d dt of x is equal to ax plus bu. Just for scalar variables, you can take the Laplace transform of vectors. Okay? And if you do that, what you will obtain is x of s, okay, let me add the hat, would be equal to a times x of s plus b times u of s. Okay? And again, I assume x of 0 is equal to 0. Okay? So, how do I take it from there? Well, first of all, I want to, since here I paid attention to x, I want to introduce the y, which will be equal to 0, 1 times x. Okay? And of course, this is true in the time domain as well as in the frequency domain. So, with this, what I can do is now see if this, where this takes me. Okay? Eventually, what I want is to get this guy and this guy to be the same. Alright? So, let me erase part of this picture. What I will do is I will erase this part first. And that part. So, my expression for A, so I will have the expression S x is equal to a x plus bu. I skip the hats. Okay, as long as there is an s, you know we are in the Laplace domain. Or in other terms, if you put this guy on the other side, I get that si minus a times x must be equal to b times u. Or x of s is equal to si minus a inverse times b times u. If y is equal to cx, okay, then I get that y is equal to c times that, or in other terms, y is equal to c si minus a inverse times b times u. Okay? So here in this case, my y, which I wanted to be x, would be 0, 1 times x. Okay? Let's see if all this math makes sense. For that, I will just keep that formula at the end and erase everything else. Almost there. I'm left with sort of a cropped expression here. So I will say it's si minus a inverse du. Okay, so let's see if this formula works. A is this. Okay, so si minus a is equal to s plus 1 minus 1 minus 1 and s. So what is si minus a inverse? Si minus a inverse will be simply one of the determinants here, so it will be 1 over s times s plus 1 minus 1 times the matrix s plus 1 1 1. Okay, so you compare s times s plus 1 plus 1. So let's see, s plus 1 times s minus 1 times 1 is this expression. It is 0 and it becomes 1 because you take the ratio of these two. Now s plus 1 times this minus that. Okay, so that's perfect. Okay, this is indeed the inverse of that matrix, provided that you multiply it by this before. Okay, all right, so I can rewrite this now, and what I can do is compute. I can now compute y is equal to. I can compute C times this matrix. Okay, so C times this matrix would be 1 over S squared plus S minus 1 times 0, 1 times this line vector, which would be 1, and then 0 times this plus 1 times that. Okay, and what we will obtain is something I do not like very much, but why not? Okay, it will be the vector. So this 1 times this plus 1 times that will be 1. Okay, and this times this plus 1 times that will be s plus 1. Now we multiply by b. Okay, and we obtain, when we multiply this by b, okay, to obtain c si minus a inverse times b, what we obtain is that this and that multiplied by 0 is 0, and therefore this leads to 1 over s squared plus s plus 1 minus 1. Okay, and what we see is that whether we compute the transfer function using direct Laplace transform or we use the state space representation, we use that formula and we apply it, we obtain the same end result. So state space representations do allow us to find the very same transfer functions as the one that we were used to computing before. Okay, now is the converse possible? Okay, so can we go from transfer function to state space? And the answer is yes, but a qualified yes. Okay, now the contents of this qualified yes will be the object of the next lecture.